Formulation. This section gives the formulation for the proposed models. Section 2.1 would present the formulation for local Euler-Bernoulli beam and Section 2.2 for non-local Euler-Bernoulli beam. As will be seen ahead, the formulation uses Galerkin weighted residual method and Hermite cubic polynomial functions, in both the cases in interest of generality. Euler-Bernoulli beam, also known as the classical beam, is known to efficiently represent a carbon nanotube, in the case when the aspect ratio, LD ratio, is sufficiently high. The governing equation for an Euler-Bernoulli beam is given by where A is the bending rigidity, W is the displacement, ρ is the mass density, A is the cross-sectional area, and the derivatives of transverse displacement with respect to beam length and time are represented by prime, and a dot, respectively. Roux used the multiple beam model to derive the governing equations for DWCNTs. It is taken as two single-walled carbon nanotubes coupled by an interaction force, represented by van der Waals coefficient, which is estimated as where sigma and epsilon are the van der Waals radius and Lennard-Jones potentials well depth, A equals 0.142 the CC bond length and R1 and R2 are the inner and outer radius, respectively, whereas and the governing equations for a DWCNT are where the subscripts 1, 2 free, I, W, ρ, represent the inner and outer tubes, respectively. Simple harmonic motion is assumed, i.e., Wjx, t equals y omega t is assumed to remove time dependency from 5, and I equals 1, 2 to represent inner and outer carbon nanotube, respectively, and omega and t represent the circular frequency and time. Using simple harmonic motion in governing equations modifies them as following Galerkin weighted residual method. Weight functions are introduced as delta W1, 2 and the transverse displacements continue to be represented by W1, 2. The weighted integral form of the governing equations is given as the weak integral form of the governing equations is eliminated by performing integration by parts, twice on 7, as given below. The boundary terms in 8, which vanish with the application of system boundary conditions, represent the shear force and moment of the beams are given by V equals A2y and M equals A few and remain similar to those of a classical Euler-Bernoulli beam. The domain length of the DWCNT is now discretized with 4 nodes and 2 degrees of freedom, DUF, per node, 1 transverse displacement and 1 slope per node, such that the present work uses Hermite-type polynomial approximations to derive the finite element formulation such that the interpolation function is given as where Ni11 is a row vector of cubic shape functions of the beam elements given by the concept of non-locality, which is accounted for with the introduction of a non-local or a small-scale factor, was extended to the field of nanotechnology by Pedersen et al., where the author applied it to Euler-Bernoulli beam model. The small-scale effect or the non-local parameter is given as mu equals E0A to consider the stress at one point of the system as the function of strain at all points of the system. This is achieved with E0 being the material constant, to be determined for each material, and A being the length of CC bond. Subsequently, researchers like Edashami and Hijabasi, John et al., and Wang and Varadin developed the model for DWCNTs using non-local Euler-Bernoulli beam model. The derivation of governing equations requires the classic Hooke's law for uniaxial stress state to be modified, taking non-local elasticity into consideration, as with sigma and epsilon being axial stress and strain, respectively. The equations of motion, perpendicular to z-axis, are given by where ρ is the mass density of material, A is the cross-sectional area, W is deflection of the beam and M and S denotes the bending moment and shear force, respectively. Using these in the moment equilibrium conditions, results in the governing equation for non-local Euler-Bernoulli beam, given as for non-local DWCNTs, the governing equations are derived to be the solution of the equations is in the form Wjx, t equals y omega t, similar to the local Euler-Bernoulli formulation. The time dependency is removed by considering the transverse displacement with respect to time as circular frequency, omega 2. To maintain uniformity in mathematical modeling with the formulation proposed for local Euler-Bernoulli model, the Galerkin weighted residual model is used for FEM, with delta y taken as weighted residual. The weak integral form of governing equations takes the form. Integration by parts is performed on the above set of equations once, and the weak form vanishes with the application of system boundary conditions. The resulting internal shear forces for both the beams are given as, and the resultant bending moments are given as. Integration by parts is performed once again on the first terms in 18, and after rearranging for clarity, the following set of equations is obtained. Using Hermite cubic polynomial functions, given in 11, the finite element model is developed. The element mass and stiffness matrices for both the local and non-local scenarios are explicitly presented in the Appendix A. And FEM code in MATLAB solves the linear eigenvalue problem, which is given as, where K represents global stiffness matrix and M represents the global mass matrix, respectively, and is achieved after assembly. Table 1 gives the element matrices K and M, which are to be assembled to form the global matrices for both local and non-local cases. Elemental matrices for local and non-local DWCNTs modeled as Euler-Bernoulli beams.